Okay, so there's two derivatives in front of us that I'd given you before, but we haven't really applied them to any of our problems. So here's our problem from your homework. Find the derivative of y with respect to theta if we have y is equal to log base 5 of 2 theta. And so I notice here that I'm going to need to be using the chain rule. My outer function is this log base 5. And so if I apply the chain rule there, I know my dy dx, or sorry, dy d theta in this case, is equal to 1 over what we're taking the log of, which in our case is 2 theta, times the natural log of the base of our log, which is 5, times the derivative of our inside. And so if we look at the derivative of 2 theta with respect to theta, that's just 2. And so I noticed that I have a 2 in the numerator now and a 2 in the denominator. So those are going to actually cancel each other out. And here we'll just be left with 1 over theta natural log of 5.
Thank you. I was really confused on that one.
Okay. So let's say I wanted to find the derivative of this y equals 2 raised to the x power, and I didn't memorize that rule over here of how to find the derivative of an exponential when it wasn't e. How I could do this really easily is use logarithmic differentiation. We can take the log of both sides of our equation. So if we take the log of, actually, instead of log, natural log is so much easier. Let's take the natural log of both sides of our equation. So let's take the natural log of y is equal to the natural log of 2 raised to the x power. So now I can use the fact of rules of logs to bring my exponent down front. And so I would have here the natural log of y equals x times the natural log of 2. So recall natural log of 2, that's just a constant. It's just a number. And so when we take the derivative of that right-hand side, x times some number, it's just that some number. In our case, this is a natural log of 2. We're going to take the derivative of both sides, and so we're going to use our implicit differentiation. And so the derivative of natural log of y is 1 over itself y times the derivative of the inside, which we're going to say dy dx. Equals, again, natural log of 2 is just a constant. So constant times x, the derivative of that is that constant. So this is equal to the natural log of 2. So let's get dy dx by itself. We can multiply both sides by y, right? And so we get dy dx equals y times the natural log of 2. But y is 2x. And so dy dx equals 2 raised to the x power natural log of 2. Which if we looked at the formula that I just gave up here, if it's the base is not e, it's itself, which we got 2 raised to the x times the natural log of the base. So I was able to get that without having that formula memorized by using that logarithmic differentiation.
Would you have to use the chain rule too if, like, say the base instead of 2 to the x is like 2x to like something?
Yes.
Okay.
Yes. Yeah, so if it had been 2, like x plus 1, we'd have to use that chain rule. Let's see, there might be something similar to that in the book. Okay, so for the following problem, it's asking us to find the derivative with respect to x, and we have the equation y equals log base 7 of x plus log base 7 of x raised to the 8th power. If I went in and did straight differentiation without rewriting this, when I took the derivative of the second piece, I'd have to use the chain rule. But we have rules of logs that we could rewrite this first. So we can bring that exponent down from that x to the 8th as a coefficient in front of our log. And so we could rewrite y as the same thing as log base 7 of x plus 8 times log base 7 of x. Actually, this even makes it easier. Notice that we have 1 log base 7 of x plus 8 log base 7 of x. So we can combine those. Those are like terms. This is the same thing as 9 log base 7 of x. And so now let's apply the derivative rule for log base b of x. So we have dy dx is equal to our 9 times whatever the derivative of this log base 7 of x is. So by the rule, it says we're going to look at 1 over what you're taking the log of, which is x, times the natural log of the base 7. So this is just 9 all over x natural log of 7. So the following, we're given y is equal to x raised to the 8x plus 7 power. And it's telling us to use logarithmic differentiation to find the derivative of this. So we want to take the log of both sides, and natural log we found is much easier to take the derivative of than log of any other base. So let's look at the natural log of y is equal to the natural log of this x raised to the 8x plus 7. So the whole point of that was so that we could bring our exponent down front. And so we have the natural log of y is equal to parentheses around that whole exponent, 8x plus 7 times the natural log of x. So now we can take the derivative of both sides of our equation. And we're going to need to apply implicit differentiation. So the derivative of natural log of y, that's 1 over y times the derivative of y, which we're going to write as dy dx. This is equal to the derivative of the natural log of 8x plus 7. And so we're going to need to apply the chain rule. Our outer function is the natural log. So taking the derivative of the natural log is...
Wait, how did it go from 8x plus 7 times the natural log of x to the natural log of 8x plus 7?
Yeah, I have no idea. Yeah, so I should have been the same over here, right? Thank you. It should have had the 8x plus 7 here times the natural log of x. Okay, so when we apply the derivative on the right-hand side, we got to use that product rule. So the product rule says I'm going to take the derivative of my first function. So derivative of 8x plus 7 is just 8 times the second function, natural log of x, plus the first function, which is 8x plus 7, times the derivative of the natural log of x. And then derivative of the natural log of x is the 1 over x. And notice I can multiply through by 1 over x. So I get 1 over y dy dx equals 8 natural log of x plus, well, if I distribute the 1 over x to 8 times x, the x cancels and I'm just left with 8 plus 7 times 1 over x, I'm going to write as 7 over x. We want to get y dy dx by itself, and we can do that by multiplying both sides of our equation by y. So the y cancels on the left-hand side, leaving you with just dy dx. Is equal to this 8 natural log of x plus 8 plus 7 over x. But instead of writing y, we were given up here what y was. Y was the x all raised to 8x plus 7 power. So instead of writing this y here, I'm going to write it as what we originally started with, this x all raised to the 8x plus 7 power. And so now we have the derivative of y with respect to x, using that logarithmic differentiation to find the derivative.